Hi folks, we're back again for our next instalment of Space Physics, and in this lesson we're going to be looking at space travel. Now, specifically what the learning outcome says is talking about the challenges of space travel, and there's a lot of learning outcomes in this section if we just go and have a look at them. Now, we can see that starting with 7.6, I am aware of challenges of space travel. So this is really, and you'll pay attention to the wording here because it's saying I am aware of, and then down here I have a basic awareness of it. And so really read the learning intentions or the learning outcomes, and almost that's the learning done, that you have a basic awareness, so you don't really have to go into much detail of this of these here, and so in this video I'm going to just talk through. I'll make up a scenario of a rocket launching off into space and then returning again, and we can discuss some of these here. But so potential across large distances by the use of something called an ion drive. We'll get to that. Catapult from a planet, maneuver in 0G, sufficient energy for life support systems, risks of takeoff, knowledge of Newton's second laws, and obviously your weight problems here. And so there's an awful lot of learning outcomes here, and probably the best way to, as I say, to deal with this. Actually, I mean, a lot of the physics involved here, and it's probably about a National 5 level for what you want to see this as. Well, if you know me, you know I love the film The Martian, and if you watch The Martian, it will basically cover just about all of this anyway. So my top tip for this is go and give yourself a couple hours off and watch The Martian. It's a very good film, and it details very accurately the physics involved in traveling to space, and it covers actually just about all of this. So we can start our story with a rocket launch. So we'll have our rocket, and a lot of the data I'm going to use of the data of the Falcon Heavy. So the Falcon Heavy has a mass of 1.42 times 10 to the 6 kilograms. Has a thrust of 23 meganewtons. Okay, so let's look at this. The Falcon Heavy is on its launch pad, and there could be a question: calculate the initial acceleration of the Falcon Heavy. And to do this, the first thing that we're going to do, and I'm going to implore you to remember this, is the first thing that we're going to draw a free body diagram. Now, we have a beautifully drawn rocket here, but this is not going to be part of our free body diagram. The rocket in our free body diagram is just going to be represented by a simple shape, whether it be a square, rectangle, or in this case a circle. And we're going to just draw the forces that are acting on the Falcon Heavy here. And so if it has mass and it's at sea level,
sorry, I don't know that one.
It's okay, Alexa, I'm not talking to you. And so it has a weight here, and that weight is going to be determined by the mass of the rocket, but it will also have a thrust. And the thrust. Now, what we're going to hope is that the thrust is greater than the weight, which will produce an unbalanced force. if thrust is greater than the weight, and indeed thrust, we'll see thrust is greater than the weight, then you're going to get an unbalanced force. And from Newton's second law, that if there is an unbalanced force, the object will accelerate in the direction of that unbalanced force. And so first of all, we can start by working out what the weight is. So we'll have our formula W equals mg. The mass of the rocket, 1.42 times 10 to the 6 kilograms. And we'll multiply that by gravitational field strength, which at the surface of the Earth is 9.8 newtons per kilogram. Take this into the calculator. times 10 to the power 6 times 9.8, and we will get some horrendous number. Eng button, if we push that, it's going to put it into a scientific notation to the closest power of 3 that it can have. So 13.916, we can move it one more place, we can have 1.39, let's just leave it as 1.39 times 10 to the power of 7, so 1.39 times 10 to the power of 7 newtons. Now we're going to look for unbalanced force, and so our fun is going to be thrust minus weight. Now if our thrust is 23 meganewtons, that'll be 23 times 10 to the power of 6 minus our weight, which is 1.39 times 10 to the power of 7. And that's going to give us, well again, let's go for here, 9.16 times 10 to the 6. Sorry, just 9.1. Times 10 to the 6 newtons. So we have an unbalanced force of 9.1 times 10 to the 6 newtons. But from Newton's second law, F equals ma. And so the acceleration of the rocket can be found by force over mass. And it's really, really important here that you realize that Newton's second law, and why I often write fun as opposed to just force, and you'll see just force is equal to mass times acceleration in the formula sheet. But I like to refer to it as fun because I want you to really, really be aware that the fun is a derived force. You wouldn't want to be using the forces that you're going to be given in the question. In this case, it's thrust. You've got to make sure that whatever you're putting into Newton's second law is the actual unbalanced force. And if there are multiple forces acting on that object, then you really, really want to make sure that it is the unbalanced one, the derived force that you're getting. And so for this, we'll put 9.1 times 10 to the power of 6 divided by the mass of the rocket, which in this case is 1.42 times 10 to the power of 6. So 9.1 and 1.42, and we will get 6.4. meters per second squared. So the initial acceleration of the Falcon Heavy rocket as it takes off, as I say, I found these numbers out from Dr. Google. It gives us 6.4 meters per second squared. Now, that ain't going to get you into space very quickly. So what's going on here? Why is it such a low value? And the reason being is that the acceleration gets larger as the rocket takes off. The Falcon Heavy, and again, blame Dr. Google for these numbers, it will burn fuel burn rate. At 1500 kilograms a second. So for every second, I think it takes about 400 seconds to burn through its supply of fuel. Every second, every instant that it goes, it's getting 1.5 tons lighter. And so you can see that from the rocket takeoff point, it's 1 point, let's just say we could say it's 1.5 million tons. That's a thousandth of the weight. So for every second that it's burning fuel, it's getting significantly lighter. And as it gets significantly lighter, because we're looking at the mass of the rocket here with the weight and the thrust, as it burns fuel, the weight is going to decrease, which is going to increase the unbalanced force and hence increase the acceleration. Okay, so that's going to get bigger, that's going to get smaller, this is going to get much bigger, and that's how it manages to get into orbit. Once it has the initial launch at its 6.4 meters per second squared, they've got to control the launch in such a way that they can get into orbit as efficiently as possible. It saves on the amount of fuel that they have to burn, and they achieve this by doing something called a gravity turn. And we'll go and we'll link over to a video that an actual launch video of the Falcon Heavy rocket. I think it was a test launch, which I've found on YouTube, and so we'll just watch that now. So here we pick up the launch of the Falcon Heavy. Now you can see in the first few seconds that it's a perfectly vertical launch, and then we've got T plus 12 seconds here just as it's starting to go out of frame. Now you may have noticed, you can certainly see in this next frame, that it is starting to tilt over, and so this is it starting to perform its gravity turn. Now the idea of this is to try and gain horizontal velocity at the same time as gaining altitude. If you remember from the section where we were looking at satellite orbits, the orbit is determined, or the altitude of the orbit is determined by the horizontal velocity. So if you have a rocket here, and you, as you would think, launch it straight up, then that does absolutely nothing for getting the rocket into orbit. And so what they'll do is that they'll pitch the rocket over in a maneuver called the gravity turn. In this way, if the rocket takes off like this, what they're doing is they're really, the main aim is to try and gain the correct horizontal velocity for the altitude of the orbit. Now obviously they do need to get out of the atmosphere, but of greater concern is to get the correct horizontal velocity, because once they have reached the correct horizontal velocity determines the altitude. It will determine the period of the orbit, which, as we know from Kepler's third law, will then determine the altitude, or the radius at which it's orbiting at. And so that's basically what a gravity turn is, that you don't fire your rocket straight up, you use gravity to kind of pull it over, and as it's taking off, you'll see this, and as you saw in the video there, that it pitched off sideways, and that's what a gravity turn is. So it's taken off, it's now in a nice stable orbit, and it wants to go and dock. Let's say it's going to dock with the International Space Station. Please note it is not drawn to scale. Okay, so you've got your rocket that's going to try and dock with the International Space Station here, and you would think you have this picture in your mind that it will, the International Space Station as is, well, let's just say for argument's sake it's flying around like this. The speed of the International Space Station, so VISS, is around about, well, it's around about 7.5 kilometers per second. So 7.5 kilometers per second, or 7,500 meters per second. So, well, let's just suppose if the velocity is directly related to the altitude at which it orbits at and the period at which it orbits at, and so on and so forth, if you accelerate your Falcon Heavy to 7.5 kilometers per second, then you'll put it here. Okay, and so now they are both at the same altitude. They're both at the same 400 or so kilometers above the Earth's atmosphere, and this seems pretty simple, pretty easy. Now you could match the launch time so that it sort of comes up right behind the International Space Station. But you've got a problem. If you launch your space rocket to dock with the International Space Station, then you're not going to, if you want it to sort of slide up right behind it, and you would think that logic would state that you're going to have your space rocket and you're going to have your space station, and as what you see in the films, you just see, well, you just drive it up to the back of it. But if they're both moving at the same speed, which they must be to be in the same orbit, as soon as you start to speed this up, what happens to it? It gains altitude. And this is the sort of counterintuitive bit with docking maneuvers of spaceships, that you have to match the altitudes, but you have to do it really carefully. And so, for example, for argument's sake, you could launch your rocket up to a slightly higher altitude, and so it's at a slightly higher altitude from here, and that would mean that it would be traveling faster, so it would catch up. And as it's about to catch up, then you can slow its speed, and so it would come up, and then as it slows speed, it would eventually come to make a perfect docking maneuver here. Okay. The second issue with docking maneuvers in space is that you don't have any atmosphere. Space is a vacuum. And so what you'll have on the sides of the front of the rocket, so let's say you've got your rocket here and your International Space Station here, so let's say ISS, rocket, and you'll have these things which we'll call retrothrusters. So you've obviously got your fiery stick that comes out the end, but you'll have gas thrusters. And these gas thrusters here, the retrothrusters, when they're in space in a vacuum, they're gonna fire out gas, and this will rely on Newton's third law. If we remember what Newton's third law is, Newton's third law: for every action there is an equal and opposite reaction. There's nothing in space. Space is a vacuum. That means there's no molecules, no particles, no gas, no atmosphere. And so how can you have anything to push on? Well, the gas thrusters will release some gas into the vacuum of space, and it's going to disperse, but instantaneously, as the gas is released, there's going to be some gas there. And the gas that's released from the thruster here is going to push, now has something to push against. So the gas here, as it's pushing out that way, so it pushes out that way, and the gas here pushes the rocket this way. And so by firing a thruster in that direction, the gas there will then apply an equal and opposite force back onto the rocket, thereby slowing it down. And so as you're up here in your higher orbit, you can slow it down until it reaches a point of where it can dock safely with the space station. Okay, we're in the International Space Station, and we've got out of our rocket. We're floating around the ISS, and we're gonna just kind of do some space stuff. So what do we need to worry about when we're in space? Well, first of all, space is a vacuum. There's nothing there. If we're in a spacesuit, that's okay. And if we're moving from our rocket into the space station, that might be fine. We could potentially jump across the gap and have like an airlock chamber that is a vacuum. But if we're going to get into the actual space station itself, let's see, what have we got? We've got some tables and chairs and things, and our TV. Then if we want to get from the vacuum of space into here, then we can't just open a door here, because the pressure difference between the pressurized living quarters and the vacuum of space, it would suddenly just evacuate all the pressure. Again, go watch The Martian. Everything's explained, airlocks and everything. So what we would do is we would go into what we call an airlock, and so we would have the vacuum. This door would be sealed. We would open up a door here. We could move from the vacuum into this chamber, still in a vacuum. We close the door, and then we can pump gas into this, but it's now sealed from the vacuum of space out here. So we've now pressurized this area. We can open the door and we can go in, and we can go and do our thing. Space is a vacuum. There's no air, there's no water. We need oxygen to breathe, we need water to drink, and so they'll have oxygen and water reclamation devices. We breathe out carbon dioxide, which is carbon and oxygen. They can separate the carbon and oxygen and re-release the oxygen back into the atmosphere here. There's water in lots of substances. Urine, they can separate the water back out from your urine. They can make new water with hydrogen and oxygen as well. And so these are certainly these are challenges which we would have to overcome if we were going to spend a long time in space. If we were going to look at a mission that would span many years in deep space without resupply at all, then we would have to have these thoughts in our minds before we left. How are we going to get air? How are we going to get water? How are we going to get heat? How are we going to get electricity? If we're on the Earth, and electricity, well, we can make electricity in a number of ways, but one of the things that you might think, well, we can go up into space and the sun's right there, we don't have any clouds, we don't need to worry about that. The sun's right there, we can use solar panels, and solar panels are used extensively in Earth-based satellites, and really that's what we will be doing. We will be using big solar panels on the side of our space station. But you should be aware that if the sun is here, and if we're looking at Earth here and Mars being here, but by the time we start going into the outer planets, and so if we get that's Jupiter, which is obviously not bigger than the sun, so by the time we start getting out to Jupiter, the sun is we're going to be so far away from the sun that it'll be less efficient to use solar panels, or the efficiency of the solar panels won't be nearly as good as they would have been if we were using them on Earth or even on Mars. And so we need to be aware of that as well. One thing, again, this is in The Martian, we have something called an RTG, which is a radioisotope thermoelectric generator. You'll basically have a small nuclear reaction which will produce heat, and the heat can then convert, it's using something called a thermocouple, will convert the heat into electrical energy, and so you'll be able to have a small battery, a spacecraft battery if you like, using radioisotopes. Back on Earth, we are shielded by our magnetic field, the magnetic field of the Earth, will shield us from cosmic radiation or solar radiation. The sun is a big nuclear reactor, and out of the sun it'll fire out a lot of radioactive material, radioactive rays, cosmic rays, which when it reaches Earth, twofold, well, the magnetic field will shield us from a lot of that, and then the atmosphere will absorb the rest. Consequently, we can survive on the Earth perfectly normally, but as soon as we go out of the atmosphere of the Earth, we lose that protection, and if we go too far away from the Earth, we'll also lose the protection of the Earth's magnetic field. And so if we go out to here, where we're no longer in protection, we need to have a spacecraft that has adequate radiation shielding. What else do we need to worry about? Well, going back to our takeoff, as was seen in the Space Shuttle Challenger disaster, you get in a small tiny capsule and you're sitting on almost 1 million kilograms of highly flammable material, and so just about anything that can ignite it is a big no-no. So you've got to be really, really careful about setting off your rocket fuel in an uncontrolled manner. That would be very bad. Okay, so well, what's next? We're going to split off into two things. I'm going to leave my astronaut on the space station for now, and I'm going to take my rocket and we're going to return to Earth. Now remember, the International Space Station here is travelling at 7.5 kilometers per second. 7.5 kilometers per second. When the Space Shuttle used to come in and do its re-entry, we were talking about 8 kilometers per second. So a rocket which is travelling at 7.5 kilometers per second, or the most obvious one of this was the Space Shuttle, because this was a reusable spacecraft. You would send the Space Shuttle up there, and it was kind of, you know what it looks like, it was shaped like a plane, that you would slow it down, and it would eventually enter the Earth's atmosphere and land on a normal runway. So we can talk about re-entry. Now the Space Shuttle, let's just say the initial velocity of the Space Shuttle, 9,000 kilogram mass, but the initial velocity when it was in orbit, we're going to say is 7,500, so 7.5 kilometers per second, which is 7,500 meters per second. Sorry, there's a wee bit weird unit. And that had to slow down to around about 100 meters per second in order to be able to land on its runway, as it would. And so initially, when it's in orbit, it has a certain amount of kinetic energy, and it must lose this kinetic energy in order to have this amount of kinetic energy. If it loses speed, it loses kinetic energy, and that kinetic energy, due to the conservation of energy, must go somewhere. And in this case, it gets converted from kinetic energy into heat energy. So we say must lose EK. We'll say therefore EK is converted to EH. So we convert the kinetic energy into heat energy. From this point, let's see, we can work out initial kinetic energy. So EK before. So EK is equal to half mv squared half times 9,000. Now, if we're talking about the Space Shuttle, I made 9,000 up. I have absolutely no idea. I probably should go and pause the video and look it up, but I won't. I've already done it now. I just made it up. What we do? It's got to be about right. Maybe. 0.5. I know you're all probably going to pause the video now and go and look it up, and then you'll shout at me. But, okay, 9,000 times 7,500. You're going to get a really big number. Don't forget to square it. We get 2.5 times 10 to the 11 joules. So it has a lot of energy. EK after, we can do exactly the same thing. We'll do a half times 9,000 times its new velocity, which is going to be 100 meters per second, squared. And that will give us, and we'll have, again, we can do this, so 4.5 times 10 to the 7 joules. That's still pretty decent amount of energy, but so times 10 to the 7 joules. But if we want to work out the energy loss, so EK loss, and we're just going to take one from the other. 2.5 times 10 to the 11 minus 4.5 times 10 to the 7. 2. I don't know why I've done 2.7. 2.5 times 10 to the 11 minus 4.5 times 10 to the 7 will give us 2.5 times 10 to the 11. No, 2.49955. 2.49955. I'm going to leave this as a big number, as an unrounded version of the number, because this energy is so much smaller than this energy. I want to actually get the accurate amount, because if we're going to then take it to the next step, so it's lost this amount of energy, and if it's lost this amount of energy, that energy has, as I've said, has had to have gone somewhere, and this is being converted into heat energy. So we will now have a new heat energy of this 2.49955 times 10 to the 11. Just as a point of note, it would be totally incorrect for you to calculate the kinetic energy or the loss of kinetic energy just by subtracting the velocities and using, well, in this case it would be 7,400. If you try and do a half times 9,000 times 7,400 squared, you will not get this answer. So this is the amount of heat energy that must be absorbed by the space shuttle itself. And it does this, it's covered in heat tiles, and these heat tiles are designed to absorb, obviously, heat. And from this, we have our formula of EH is equal to Cm delta T, so our specific heat capacity formula. And if we know the amount of heat energy that is gained, and we know the mass of tiles, and we know the specific heat capacity of the tiles, we can work out the temperature rise of the tiles. Okay, and I'm not going to do an example calculation of that, but if you look in the problem books, I mean, you'll have done plenty of specific heat capacity calculations, and there will be problems in a problem in the problem book which asks you to work out the rise in temperature of, I think it's talking about the rise of temperature of an asteroid rather than heat tiles of a space shuttle. Okay, right. We have landed our spacecraft. We have absorbed the heat energy, it's been dissipated in heat tiles. The spacecraft is now back on the ground. But don't forget, we left somebody on board. Now, why did we leave somebody on board? Well, the answer is because this person, let's call them Todd. Todd is a good astronaut name. I should have called him Mark after the Martian. So Todd is going to go on a journey into the far reaches of our solar system. So here is Todd on Earth on a massively oversized ISS. And Todd has a rocket. So Todd gets on his rocket. It's a pity his rocket is not quite big enough to fit all of them inside, and his head is unfortunately sticking out the top. But you know what? It's okay, because there's no air resistance, and so he's not going to get blown around. He just won't be able to breathe, and it will be rather cold. But never mind Todd, he'll survive. So they launched the rocket, and the plan is that if our sun is over here and Earth is here, we're going to not go to Mars. Mark Watney went to Mars, and that was bad. We're not going to go to Jupiter, because Jupiter is just big and gassy and boring. We're actually going to go to one of Saturn's moons called Titan. We'll go to Titan. Titan, which you can't actually see, kids. You still can't see it. Let's find Titan. There we go. Okay. So, you launch the rocket off. Now, initially when the rocket is launched, you can use gas thrusters or chemical rockets. And it'll be able to accelerate using these chemical rockets. And the thing with space travel is that once you're traveling at a certain velocity, you're going to maintain that velocity. Because it's a vacuum, because there's no air resistance, whatever speed that you start off going in the direction that you're going in, you're going to just keep going in that direction forever until you get into the gravitational field of something else or whatever. But in theory, in realistic terms, you could just be traveling forever in a straight line at constant velocity, a la Newton's first law. You'll continue to travel at a constant speed unless some unbalanced force acts upon you. And so after this initial firing of the rockets, we can't burn our rockets for years and years and years, because as you've seen from earlier, we're going to burn 1,500 kilograms of fuel per second, and you would need an awful lot of fuel to keep burning that fuel again and again and again, and it's just impractical. And so for long distance travel, for interplanetary travel, certainly from outside or anything beyond Mars, Mars is just about close enough that we can burn some rocket fuel and we can be on our correct trajectory just to get to Mars with conventional rocket based spacecraft. But if we want to go further afield, well, we can either take a really, really long time about doing it. We can just accept that it's going to take us a long time to get there, or we can develop new technology to propel our rockets. And one of these is what's known as an ion thruster. And the ion thruster, the basic understanding of it, and I really just want to give you a basic understanding, is it will fire out, so you'll have your rockets your ion thruster, and it just fires out tiny, tiny charged particles. And as per Newton's third law, the charged particles will repel from each other, so the charged particles from here and here. What you end up getting is a tiny acceleration, and you get a really, really small acceleration, but that acceleration can be maintained for a very, very long time. Okay? And so rather than having a large acceleration with a chemical rocket for a short period of time, you get a very small acceleration but for a long period of time. And the net effect is the same. It's every single time you're accelerating, you're increasing speed. And if it's in space, if it's in a vacuum, you don't slow down. Okay? You can also use planets to help you. Now, if Jupiter, let's say you're going to have Jupiter here. Now, Jupiter is moving around like this, and you want to go and get to Saturn, which is over here. If you take your spacecraft, because Saturn is moving this way, if you fly around in the correct way, you can get what's known as a gravitational slingshot or a gravity assist. If you go around in the same direction that the planet is moving in, then you're going to get this gravitational slingshot. It's going to accelerate the rocket by getting sort of temporarily captured in the gravitational field of Jupiter, and it's going to increase your velocity. You can also slow your rocket down in much the same way, that if you try and go against, so if you come around this way, then you can go against the motion of the planet and you'll get slowed down. So get slow or get fast. Okay. Now, I think that's pretty much it. What we'll do is we'll just look at the learning intentions again and just make sure that we have done everything. So we're aware of the challenges of space travel. Well, you've sat and listened to me for probably nearly an hour drone on about space travel. So large distances, high velocity using an ion drive, producing a small acceleration for an extended period of time. Traveling large distances through space can use a catapult from a fast moving object, asteroid, moon or planet. So that's the gravity assist, or the gravitational slingshot. Astronauts maneuver spacecraft zero friction environment, dock with the ISS, yep, good. Sufficient energy to operate life support. So we could use solar cells, but we're aware that solar cells are less efficient the further away they are from the sun. We could use something different, such as an RTG. The Newton's second and third laws in their application to space travel, rocket launch and landing. And we can use W equals mg to solve problems involving weight, mass, gravitational field strength. Different locations in the universe. Well, we haven't really talked about different locations in the universe or different locations in the solar system, but we've done that before, and you should be fairly comfortable if you're having a question about G on a different planet or place. And if I go back to the data sheet, where have we got gravitational field strength? So for example, if you're looking at doing calculations involving weight on Mars, you would be using 3.7. That's us for the second video of space. I hope you have made it this far to the end, and thank you for watching, and I'll see you again soon. Okay, bye.